Okay, let's get started. Hi, everyone. I'm Kevin, one of the head TAs of the class. Richard is still away this week, so this lecture, we're very excited to have Chip, who has, for the last 2 years, been teaching a class on TensorFlow, give an introductory lesson about TensorFlow, how it works, how to use it. For the next 2 assignments and the final project, you'll be using TensorFlow, so no more fighting with gradient checkers, which I hope you're all happy to hear. Just 2 announcements as a reminder. Number 1, assignment 1 will be due tonight at midnight, and then with 3 late days, you can push the deadline back to Sunday at midnight. Also, assignment 2 will be released tonight sometime after lecture. And with that, I'll leave it to Chip.
So hey everyone, I'm Chip. I'm teaching TensorFlow Deep Learning Research, cs220 at Stanford. And actually I took this class about 2 years ago and didn't do very well. So I'm still very nervous talking here. So I'm from Vietnam, and if it's, I know I have an accent, and sometimes I talk really fast. If at some points that you think that I'm incomprehensible, just wave the hand so I can slow down. Okay, so today we have a lot to cover, so I just hope that we can go over everything today. So we start have a very brief introduction, justification of why we are choosing to do a tutorial on TensorFlow and not like PyTorch or other things. We have to go over graphs and sessions, which Kevin told me that you guys are very familiar with. We're going to do some simple example, linear regression. We learn Word2Vec, and we learn quantitative data and structuring the model and managing experiments. So I think Kevin sent out an email to bring the laptop because we'll be doing some live coding, so you guys can follow along. Okay, so what is TensorFlow? So when choosing a frame, so there are a lot of frameworks out there. If you notice, somebody just recently did a calculation, and on average, every week there's a company or another release a deep learning framework. So out of there's so many of them, why did we choose TensorFlow? So when we choose a framework, we choose something on both flexibility and scalability. So for flexibility, it means that for doing research, you would like to create something very novel, and you would like to have a framework that with some kind of structure or functions and classes that allow you to combine them in a novel way to create new things. And scalability is when you do in production, you would like to be able to deploy it like to many different GPUs or data center. So there are many frameworks, for example, like PyTorch that has wonderful flexibility, and a lot of researchers choose to use PyTorch instead. But PyTorch is not very good for production. Or other framework with a lot of good scalability, like MNX, but it's not good for research. So TensorFlow is a sweet spot because it was created by Google, and they try to have a single framework to streamline from research to production. And because of that, sweet spot that TensorFlow has become very popular. If you just by the number of repository on GitHub, you can see that TensorFlow is the number of repos related to TensorFlow is twice as many of all the other frameworks combined, and the same with Archive. So when we start, so to start is just like importance of flow. So for this tutorial, a lot of examples are using TensorFlow 1.4 version, but I think it applies for everything like above 1.0. And we for the code I will be writing using Python 3, but I think for Python 2 it still works if it's an import feature or something. Okay, so for graph and sessions. So the most important thing to learn about TensorFlow is that it separates computation, definition of the graph from the execution. So what does it mean? That every TensorFlow program has two phases. The first phase is going to assemble the graph, and the second phase is going to execute on the ops in the graph. So this might change in the future with eager execution. But I was thinking of whether to introduce it, but we were doing some benchmarking with eager execution, and it's pretty slow. For some on Word2Vec, like 8 times slower. So I think it still take a few more, like maybe half a year until eager execution actually like fluently, like very useful. So for now, I think we should focus on without eager execution. So Yeah.
Can you say that again? That last thing you said?
Oh, so it's still like with eager execution. So it doesn't separate between assembling the graph and executing it and executing it. So but we do some benchmarking with eager execution, and it's still very slow. Like for Word2Vec, it's 8 times slower. So we decided that it's still like maybe like 1 or 2 more quarters until eager execution is up to speed with the normal version. So we focus on normal version instead for now.
Sorry, a quick question. So, like, how is the eager model not separating the physical entities?
So they did something with the repeat question. So he's asking that why eager execution doesn't separate between the two things. So it's because so TensorFlow is a backend in C++. So originally TensorFlow was created. So I was talking to them, like asking why didn't they do that in the beginning to make it easier for people to use TensorFlow, and to saying that with building by separating like graph and executing it, there's a lot of room for optimization. So you can do all of the buffer, reuse buffer, and make it like a lot faster. So, but after a while, a lot of researchers, they complain about to make it like very hard. It doesn't have the flexibility of like dynamic graph like PyTorch. So TensorFlow starts switching to it, and it's still so they do it by just like calling execute on the C++ code underlying directly, and it has a lot of overhead handling, and it doesn't allow for the optimization when you separate the graph and the execution of the graph. So that's why it's still slow right now, but they are aggressively on it to make it faster. I hope they answered the question. So the first thing is, what's a tensor? Anybody has an answer for this? Yeah, you want to say something?
It's like a NumPy array, right?
Yeah, so tensor is basically just an n-dimensional array. So for example, like a one-dimensional tensor is just a scalar, or one-dimensional tensor is a vector, and 2D tensor is a matrix, and so on. So let's try to see what does it mean when people say data flow graph. So you can start writing some code like this. So you import TensorFlow and you create an add operation. And if you visualize it on the board, you can see something like this. So if you see on TensorBoard, you see that it's just x and y. So actually, it's not 3 and 5 because TensorFlow automatically names all the nodes when you don't explicitly name them. So it's different from the normal graphs that we use because for normal graph you have like on the nodes are the values, and on the edge are the like operation like connecting the values, right? But in TensorFlow, on the nodes are operations and variables and constants, and on the edges are the values of the TensorFlow, like the tensor store. So the TensorFlow actually means a data flow because they like flow the data between the ops. So yes, that's where the names come from. I was very excited when I learned about that. So if you try to print out A, you can see that A is a tensor, and it's not a value of 8. So to get the value of A, what you have to do is that you have first to start to create a session and assign. So you create a session, and within the session will allocate the memory to store the value as a variable. So what it does is that it does something like this. So you create a session, and then you execute the variable A within the session. And when you print out the value, you can see that print out 8. So what a session does is that when you run a certain op, in this case is a op named A, it will look at the graph and say, how can I get this? How can I calculate the value of this op? And it will look at the graph, and it was just like, oh, so to get op A, it will have to like add 3 and 5, and then it output it. So if you do in the more patterned ways, then you can just like create a with block, so you don't have to so it can close a session for you. So a session object encapsulates the environment in which operation objects are executed and tensor objects are evaluated. And it's very important because session actually handles the memory. And by default, like each session tries to grab as much memory as possible. And when I was teaching my class, I saw a lot of students, they have this bug. It's like their program just hang. It's because when they open a session and they forget to close it, or something, and they create another session. And both sessions will try to grab as much memory as possible, and it will hang the program. So try not to have like more than, try not to have like multiple sessions running at the same time. Yep. So again, more graphs. So you can see like if you have a little bit more complicated graph like this, so you have like multiply and add and power. So what it does is that so you can see it. I named this one useless because you will see I only like execute the power of, and the value of the power of doesn't depend on the value of useless. So the TensorFlow actually never calculates the value of useless. So when you execute the value of power of, it will only look at on the computation that power of depends on. So it can save a lot of computational power when you run the program because, yeah. So another good things about the graph is that you can divide the graph into different subgraphs and put them on different machines. So on a notable example of it is when you do like AlexNet. If I'm not mistaken, it was a winner of ImageNet in 2012. Right. So what they do is that we have like 96 filters, and they put them, like divide them into different GPU to make it faster to run the model. So yeah, so like how do you with distributed computation? So if you have more than one machine, or so you can have you can just use a keyword with tf.device, and it just put the device that you want to put the computation on. So in this case, you have like GPU 2. So actually, it's a third GPU. Yeah, I'm trying to graduate, so I just have GPA. Think of it a lot. Yeah, so that is how you want to distribute computation. So yeah, so the question is like, why do you need to use graph? So the first thing is that you say computation. TensorFlow only runs the subgraphs that lead to the values that you want to fetch or the ops that you want to execute. So second is that it can break computation into small differential pieces to facilitate auto-differentiation. So TensorFlow, as well as a lot of modern frameworks, does auto-diff. So it does so you only need to build a forward path. You just need to define on the computer on the inference, and it will automatically does on the differentiation for you. And the next thing, the third reason is to facilitate distributed computation, to spread the work like across different machines. So TensorFlow does not really work with CPUs and GPU, but you can also work like you can also put it on Raspberry Pi or also on a mobile platform. And of course, like a lot of our machine learning models have already been taught in graph, so just visualizing it in graph makes it easier to understand. Okay, so I think the next thing that any questions so far? Or should I just move on? But if you have any questions, just feel free to ask. So I think TensorBoard is really important, and it can help a lot with a program. So I just want to introduce this as early as possible. So yeah, so when you have something like this, so you have like just three op, like A, B, and X. When we want to actually, so when we want to write our graph to TensorBoard, we first need to write to some kind of like event file or like log file. And so we use it by using a file writer. So we can create it in either location. So the first location is that like just right after you compute the graph. So like when you create the file writer, the first parameter is where you want to store the graph, and the second is the graph that you want to write to the location. So if you just create just outside this session, you just access by calling the tf.getDefaultGraph. So you can just write the graph you're working on to that location. And if you write it like within the session, then you can just like write the graph that the session is running on to it. Either way is fine, and you can close or write it after you finish using it. So after you do this, and you remember that we write that to graph folder, so we can run the program, and now you can just use this keyword, the TensorBoard log directory, GB graphs, and by default it opens to port 606, but you can just use any ports that you want. So if you go to the and then you open browser, open browser, and you will see something like this. It not only can visualize our graph, it can also show the training progress, and later on you can see something like embedding projection, which will be really useful. Okay, so next we'll cover some of the basic TensorFlow ops. So the first thing is constants. We have seen that creating constants is pretty straightforward. So you can create, you can just like create constants. And also like TensorFlow support broadcasting, very similar to NumPy. You also have some kind of ops to make it easier for you to create tensor of certain value like zeros, or you create zero-like. Then you just create a tensor that's similar to with the shape and the type of another tensor, but fill everything with 0. So yeah, you also can create like constants as sequences, like a linspace and range. But remember that tensors are not iterable. So if you say anything like for something in tf.range, for as in NumPy, it will not work because you cannot iterate tensors. And of course, it will also change with eager execution, but we are not covering it right now. It also can create randomly generated constants, which can be very useful for when you initialize or the weight. And one important thing, another thing is that a lot of people, when they try to replicate other work, sometimes it's hard because there's a lot of randomization in the process. So one practice is just like to have a certain seed so that to make it easier to replicate the result. So you probably notice that there's a lot of similarity between TensorFlow and NumPy, and actually TensorFlow was designed to integrate seamlessly with NumPy because NumPy, after all, is a lingua franca of like data science. So if you actually like the TensorFlow type and NumPy type are interchangeable. For example, like when you print out like tf.int, it's gonna be the same as numpy.int. Like if you like equal NumPy, it's gonna return true. And also like you can also like initialize or tensor with NumPy type, like initialize with the tf.1 with the type np.float. And one thing is that like after you execute some variable or some ops on sessions, the value it returned will be NumPy and not TensorFlow type. For example, like A originally is a tensor, but after you execute it with in the session, it will be a NumPy array. So even though TensorFlow can integrate similarly with NumPy and also sometimes with Python native type, for example, it can take in the string and integer and float, but always use TensorFlow type when you can. For the reason is that for Python native types, doesn't, for example, like the types in Python are very dynamic. It doesn't, for example, so like when TensorFlow has a float, it doesn't know whether it's like 32 or 64, and TensorFlow has to infer that, and sometimes it can cause trouble. So you always try to be as specific as you can. And also with NumPy arrays, one big problem with NumPy is that it's not distributed. So so if you want to make the computation like GPU friendly, working on GPU, like distributed, then you should probably use TensorFlow type instead. So we learned about constants, and so what's wrong with constant? So the first thing is it's not very trainable. So for example, like when you have like some weights and biases, you would want the weight and biases should be updated during the training, but with a constant, it will not happen. Does anybody know there's another reason why constants should not be used? Does anybody know? Does anybody have a guess?
They're passed on by reference?
I think actually no. Maybe I don't know. Maybe it's underlined. So the key thing is that with constants, it's a stored in the graph definition. For example, like if you declare the constant or something like this, and you try to print out the graph definition by just do it like .sGraphDef, you can see that's a tensor content. So we actually store the content of the constant in the definition. So the problem with that is that like imagine you have a very big matrix and you have like millions of entries in the constant. It will cause the graph definition to be really slow every time you want to like start a graph or reload the graph or something like that. So only use constants for primitive types like integers or float. But when you have like multi-dimensional tensors, then you should definitely use something not constant. In this case, it can be variables. So for variables, there are two different ways when you can declare variables. So you can just simply like dot type variable, just simply like say the initial value and the type if you want, and also like the name. There's another ways when using tf.get variable, and we will learn about the different briefly in the next few slides. But basically, like TensorFlow discourage the use of tf.variable, and they encourage the use of tf.get variable instead. So to use variables, you have to initialize the variable. So you remember that variable is just like, so remember that session actually is the one that allocate memory to store value of variable. So you have to tell the session that like to initialize on the variable before you can access them. So the easiest way is you just initialize on variables at once by using tf.global variables like initializer. You can also initialize only a subset of variables by doing something like this. So you can like, I want to initialize only A and B. Or you can only initialize a single variable. But I almost never use the last two ones. I only use like the global variables to make it easier. So first of all, like if you want to get the value of, so like if you print out the value of w, you can just like, it's the same case as a constant. You can just get a tensor. You don't see the real value of w. To do it, you can have to like dot eval. I think I missed a slide here. So to do it, you have to like run like w.eval, and it will show you the value of w. So here's a question. So you create a variable w with initial value to be 10, and then you want to assign the value 100 to w, and then you initialize w, and then you evaluate the value of w. What do you think we will get when we run this? 10? Why do you think it's 10?
You only run the initialize.
Yes. So yeah, you're right. So what it does here is that so w.assign 100 is also an op. And for that op, so like when you do it, it will create an op, but it doesn't execute that op. For that op, for the assign to take effect, you have to execute it within a session. So you have to do something like this. So you create an op, like w.assign 100, and then you execute that op within the session. And now when you print out w, you will get 100. Okay, I think that's it for constant and variables. So the next thing we will need to deal with how to like, okay, now you create a graph, and how can we just import our data so that we can train our model. And one way to do it is using placeholder. It's an easier way. We'll learn about a different way after. We will learn about another way after this. So just a quick reminder that a TensorFlow program often like has two phases. So first, when you assemble the graph. And the second is like when you just execute the graph. And it's similar to, so you can actually assemble the graph without knowing what kind of values we are dealing with. So for example, like imagine when you define a function like f of x and y, something like this, like the 2 times x plus y. So you can define the function without knowing what's the specific value of x and y. And only when we do the computation that we supplement the value of x and y. And for example, we like, oh, x actually equal 1 and y actually equal 2. Then we have something like fx and y actually has a value of 4. So yeah, so x and y are, in the case are placeholders for the actual value. And it's very similar in TensorFlow. So it's, why placeholders are really important because, for example, like when you build a model for a client, and the client has their own data, and they don't want to give you all the data, so they can give you a subset of the data, and you can train the like test a model on it, and then you can give the client gives the client just a model, and they can supplement their own data later on to test it. And also very helpful for testing. Like you can just use some dummy data where you know the exact inference, and then you can test it on the dummy data to see whether our model works on the dummy data or not. So to create a placeholder, you just need to specify type and shape, and also name, so TensorFlow knows what name it is to display on the graph. or you can clone it later. So first of all, you create a placeholder of a float type, and with a shape of 3 means that it's a one-dimensional tensor, has a shape of like 3, and it doesn't have a value of 3. And you have a b as a constant with a value like 555, and you can use placeholder as you would with any other op. So like C is a sum of A and W. So what do you think we will get when we print out, when we try to like get the value of C? I mean, yeah, it's an error because it will look like, okay, so we need to get the value of C, and C depends on A, but we don't know what the value of A is because A is just a placeholder of the real value. So if you want to get the value of C, you will see that error if you forget to supplement or data to placeholders. So to supplement the values to placeholders, we use something called a fit dict. It's actually a dictionary that maps the placeholder to its real value. For example, you want to map, like you want to give A the value of 1, 2, 3. Then you just like have this fit dict, and you can, when you print out C, you can get 6, 7, 8. Yeah. So one thing that when you notice, like in placeholder, you can specify the shape as none. So none is really useful in many cases. For example, like when you have different batches size, you have like, so you don't know like what is the batch size you want to use yet. So you can have like a very flexible shape for the number corresponding to the batch size. But it also means that, but it can also be very tricky when you try to debug, because like it takes in everything and it doesn't tell you like, oh, this, you're not supposed to fit in data of this dimension or something. And another problem with when you're using shape equal none is that when shape equal none, it like on the tensor doesn't have any rank anymore. And for a lot of operation, especially for matrix operations, it would require you, like it will only work with tensor of specific rank. And when you have shape equal none, those matrix operations will not work anymore. So sometimes you can have like shape equal none and say, oh, the tensor is not of, like it only work with rank above 2 or something, and it's probably because you have some too flexible shape in the definition. Okay, so if you visualize it, you can just see like placeholder is just an op, and like the number you see on the edge, like 3, is the shape of the placeholder and not the value of placeholder. Okay, so when you train the model, often you, yeah?
If you want to, if you know that you're going to have, I don't know, a batch size n, you don't know in advance what size n is going to be. Can you declare n kind of outside of TensorFlow and then refer to it within TensorFlow? So, okay.
That's often so like you have a batch size like maybe 128 and just declare it to be batch size. But usually like sometimes when you train, you have like multiple, you have a batch of like a lot of, you want to train multiple samples at once. But when you test, you might want to test only one sample. And you want the graph to work on both like of the batch setup and like the single sample setup, and you want that to be like non, the dimension to be non. Yeah.
So in terms of like the shape inference that TensorFlow does, you can just give it a like a Python variable as like n, and it will figure everything out.
Yeah. So when you train, you might have like multiple batches or multiple samples. So if you want, you have to like using fitdex, you have to have like, you just like to fit them in like one at a time. So you usually use a for loop. You can see it a lot in the training loop. Yeah. So it's good for testing. You can probably like use it at some point in the class. Okay, so I think we just cover on the basic building blocks of TensorFlow. So I think it will be more useful to actually go through a couple examples so you can get familiar with the framework. So for the first example, it's going to be very straightforward, very simple, maybe like 10 lines of code. We're going to do a simple linear regression in TensorFlow. Yeah, so you're pretty familiar with linear regression. So you have like some dependent variable y and have some explanatory variable x, and you try to find a relationship between x and y. In this case, it should be linear. For example, like recently I was I saw this visualization. It's pretty cool. So on the x-axis is a life expectancy, and the y-axis is a fertility rate, which means like the average children the women in the country has. And you see that there seems to be a pretty strong linear correlation. Seems like the more children you have, the more likely you're going to die or something. Okay, I think I should have said that it's not very politically correct, but you can see the relationship. So we're just wondering, like maybe we can try to find that relationship, try to determine what that relationship is. So we just have the x is the birth rate, and y is the life expectancy, and we have our data. I think our data is in. Kevin, did you send the data to the student?
Yeah, so if you want to follow along on your own laptop, in the syllabus next to the slides for the lecture, you can download the code that we will go over through here. I think you'll also be doing it on the projector now.
Yeah.
So this is optional, but may be useful.
Yeah, so on the starter code, I want to comment the different steps that you can just like do on your own as well. So we have like 190 points. So for simplicity, we only deal with the data in 2010, which has 190 countries, and with a birth rate of and life expectancies of those countries. So once we find the relationship between x and y. So inference is pretty straightforward. We just like it's just gonna be a linear one layer, and for the loss, we're gonna use a mean square error, something like this. So yeah, here's the data. Let me show you what the data look like. So here's the data, and so yeah, so the country, so the birth rate like this, and the life expectancy, and you can see they are all just float. Let's see. Yeah, for the starter code, you have the linrect starter.py. Is this one? Yeah. Can you see? Is it too small? Oh, and for this, I usually have this because if you just install the TensorFlow using pip, then it will not be compiled according to some like to take advantage of LA, like some optimization to do arithmetic computation on TensorFlow. So you can tell the warning, and when you by setting this log level to be 2, so the warning will go away. It's still there, you just don't see it. So yeah, we'll be going over some of the steps. So the first step is just reading the data. So data. And get the data into a NumPy array, and we get the number of samples. So first, it just creates a placeholder for x and y. So remember how to create a placeholder. Let's see. I think I have like step by step here. So yeah. So the first phase is a sample out graph. So step 1, reading data. Step 2 is you want to create a placeholder, something like this. So for placeholder, we have like the type, the shape, and maybe the name. So what is going to be the type of this? I think it should be float, right? I think that all our data is in float. So let's say float. So shape is just scalar. So you can just do something like this, and name maybe x. And the same thing for So for create weight and bias, so you can do it either with tf.variable or tf.getVariable, and we're gonna use getVariable. Do you remember what we have to do here? I think so. The first one is just weight. And you can use initializer. So you have to specify shape as well, but when you do the constant initializer, then we don't have to specify shape because it just takes the shape as a constant. So for this, you just use like 0. Where is this? Sorry, just the constant. Yeah, so same thing with bias. For the predict, our inference is just simply just that. And for loss square, for the square loss, we use something like this. We can name it. So if we want to visualize our graph, then we should create a file writer. So you can do something like this. Why does it suggest me something wrong? So the first one is just where you want to store the graph. So maybe in this one, I just want to store it in the lindrec. And how do we access? How do we access the graph to write into this folder? Get the full graph, yeah. So step 7 is just like first, because we create some variable, to use those, we have to initialize them. So we do it by So and now, so we train us here. Here's a training loop. So we just like do it for 100 epoch, and for like x item x, y, and data. So what we have to do is that So first we have to run the optimizer, and the second is that we have to get the loss. And what else we have to do here? Feed in, right? So we need to feed. So we're gonna try to get like feed x with the value x here, and we place order y with the value y here. Do you see any problem with the code? Do you think it will run? So I did it on purpose. So actually, it will not run because the loss here. So remember, the loss we define as a tensor, right? It's tensor op. But after we execute it through a session, it will return a numpy array. So in the next iteration, it will try to execute which is a numpy array, and it will say like, oh, we cannot do it. So easily we do something like this. We just do something like this. So just like doesn't change the type. Again, have to close the writer after we're done. Yeah, if we want to visualize this, then we probably want to get the value of w and v. And here we can comment out. Well, I hope it runs. Let's see if it runs. Yeah, oh no, I think. Was this like? Yeah, it's running.
Can you show us your code again?
Sorry?
Can you get back to your code? What did he change at the end?
What?
What did he change? Just the last step?
Yeah, that's a loss because I don't want to name it the same name as loss here because it will change loss type. Yeah.
At what point does it do the gradient percent?
Yeah, I think we're about to cover it in the next session. So what it do is like, so when they execute the optimizer, so let's see how we define the optimizer. So optimizer is just it follows the gradient descent rule, and with the learning rate of this, and the goal to minimize loss. So when we execute optimizer, the session will think, oh, optimizer will try to minimize loss. And here's a loss, and like loss depends on y prejudice, which is like depends on like w and b. So it will update w and b. We will cover it in the next new slide, in the next few slides. Because I didn't want to like just introduce everything at once. So after you finish running, you can see the here's a predict data, which seems to be a pretty good approximation of the data. And actually we print out the value, and it seems like the W is to be about like -6. So on average, having a children costs you 6 years of life. That's pretty not true, but yeah, I think this is a classic example of correlation doesn't mean causality. I don't think having children actually costs you 6 years of life. So feel free to have as many children as you want. Okay, I think for the next step, let's see. Yeah. Yeah.
So for the file render part, and on your slides you have like cs.graph that's also written to the same file.
Oh yeah. So wait. I'm sorry. Yeah. Okay. Let's see. So let's see what it looks like on TensorFlow on TensorBoard. So is it too small? Yeah. So let's say TensorBoard log there. Okay, so I will go to localhost to see our graph. It's a bit slow. So here's a graph for it. Yeah. So you have bias and weights, and you can see like gradient descent here. So you can see the gradient descent update and weight and bias, and also output gradient. Yeah, we will cover it a little bit more. Okay, then we can go to the next example. Oh yeah, there's here. So you can see that what we did here is that we use placeholders. And there are a couple of problems with there are a couple of problems with placeholders. So actually, placeholder is really good because it puts the data processing outside TensorFlow and it's in Python, so you can do anything you want in Python with it. And if you're already familiar with Python, then it's great. So the problem is that usually often end up doing this. So you know that doing multi-threading in Python is not really easy. It's not very easy. So people usually actually just end up doing like one single thread for it. So it's very hard to optimize the code because there's a bottleneck in the data reading. So you can see like what happens in placeholder is that first you read, you have to place placeholder, and then every time you train it, you have to like feed in, you read in from like the Python like or NumPy where we store it into the TensorFlow program. So it creates bottleneck. So there's we're thinking like instead of like having to read in our data every time we do it into our placeholder, is there a way we can just do our inference directly on the data instead of on placeholder and then supplement data into placeholders. So TF.data is a way to do it. Actually, I think it's a second-ish attempt of TensorFlow to make something easier to use with data, because before they introduced something like queues and data readers, and it was awful. Like the program just crashed all the time. So TF.data is something they promise to be easier to use, and it does a lot of data reading optimization for us. So for TF.data module, so we have two main things, like the dataset and iterator. So dataset is just how you store the data. So it can create a data either from tensor slices or from generator. Like for example, you have a NumPy generator or Python generator, you can create it from it. So for example, in our case, we would want to create from tensor slices. So remember, our data is actually a NumPy array. So the first column is X and the second column is Y. So we just create like, so the first column is the features and the second column is the labels. So you can create a data set like this. So if just like for sanity check, you can just like print out the output types and output shapes to make sure that it's what we expect. So you can see that, oh, the type is float for both, and also like the shape is just scalar. So you can also create data set from files, like text-line data set, which is very good for textual data. For fixed length record data set is, for example, when you have data when each entry is the same length, like when you have the images, like every image is like 28 by 28 or 32 by 32. So tape record data set is when you deal with a specific data type on tape record that is some sort of like, I think it's binary file that's compatible with TensorFlow. I don't think we have time to cover that, so I'm just like introduce it, and you guys can look them up online. So after we create a data set, we need to create an iterator to iterate through the samples in the data set. Oh wait, until what time is this, the class?
5:50.
Oh, okay. So you can create an iterator. So there are two ways to create iterators. The first is to make one short iterator, which will just create iterator to go over the to go over the dataset exactly once. So you don't have to initialize it. You just it's just run until the end until the end dataset and it's finished. You cannot restore it. You know that it doesn't. It's difficult because oftentimes you want to train the model on the dataset multiple times on different epochs. So you want something that after the iterator reach the end of the dataset, you would like to reinitialize it to go back to the beginning, so you can retrain, you can train the model another time. So that's what you do with initializable iterator. So yes, that's what. So if for any initializable iterator, you would need to initialize it every time you restart the epoch. So if you start something like this, if you print things out, iterator, dataset, make one short iterator, you'll select X and Y. Instead of X and Y are not placeholders anymore, it just gets the next item from next entry from the iterator. And we print them out, you see that, oh, they actually print out the next items in the dataset, just for sanity check. And when you trained, so it's really, so the first, at each epoch, at the beginning each epoch, we would have to initialize it, and you have to, and you just run optimizer without no feedback at all. But there's one catch here is that I don't know why TensorFlow doesn't do it for us, but you would have to catch when it reaches the end of the iterator, the end of the dataset, you have to not do anything. So you just try to get the next element from the iterator, and until the element until there's no more samples, and just return. So out of range error. So that's what you have to do with the try step. So yeah, so you can also do some data handling in TensorFlow, the dataset when you want to shuffle it, or you want to repeat it, or you want to sort of batch it into a certain batch size you want. You can also map each element dataset to another type. For example, when you have the just an index of words, you're going to want to map it to one hot vector, then you can just do something like this, which is pretty straightforward. So yeah, so let's try to see how our code looks with dataset. So we'll go to the next dataset. You can see here, it's pretty much exactly the same on the step as the same, but instead of doing on placeholders, you do it with X and Y, the sample from the dataset. So actually, if you run it, so what I did at home is that I run each model with placeholders and with datasets 100 times. And on average, with placeholders, it takes 9 seconds. And with ts.data, it takes about 6 seconds. So we have about 1/3, 33% increase, decrease in time, which can be a big help. So yeah, so Kevin, Kevin Clark here, he suggests that we should add this slide. So whether should we always use ts.data or not. So for prototyping, predict can be a lot faster and easier to write because it's in Python. Also, ts.data also tricky to use when you have complicated processing, pre-processing of the data, or when you have multiple data sets that you want to fit. And also for a lot of data in this class, at least, a lot of things just deal with indexes of words. So it's just so data is just integer. So it's not, ts.data will not offer a big increase or decrease in time or increase in performance. So yeah, you feel free to use whatever you feel like using. I see a lot of people using TF placeholders. For me personally, I like ts.data, but it's why you want to use placeholders. So yeah, so that's what somebody just asked about how does TensorFlow know what variables to update. So we go over optimizers. So when you declare something like this, it's just basically tell. So you tell TensorFlow what kind of update rule we want and what is our goal. And the practice usually use minimization. And so you execute the optimizer, and you can feed in the data if you need to. So session will look at untrainable variables that loss depends on. So it will only update variables that you want to be trained. So maybe not in this class, but in a lot of models that you will not want to train the models. And I often see it more in computer vision and also in reinforcement learning. But I don't think in this class you will actually have something that is not, you don't need something that stays like constant through the training. So like when you create a variable, you will have a trainable equal true or false. By default, all variables are trainable. And they have a lot of different optimizers in TensorFlow. So I think, I'm not sure if this class cover like what optimizers should be used. But they're like, I think there are really good blog posts comparing different type optimizers. And usually Adam works like out of the box like better than other one. Okay, so I think you guys have already learned word2vec, right? So I think it might be a good example to do word2vec in TensorFlow as well. So the first thing, before we go into the code, I just want to like go over a couple of things. So first thing is embedding lookup. So we have like one hot vector, and you want to get the embedding corresponding to that. So it's basically it's similar to just do a matrix multiplication. So in TensorFlow it's quite easy. So you take in like the params actually is the matrix, and the ID is like the index of the matrix where you want to get the rows of it. And also in class you learned negative sampling. So negative sampling is actually a simplified version of what is called a noise contrastive estimation. So in the original paper in Skipgram, Mikolov showed that negative sampling has a pretty good performance. But there's one thing about negative sampling is that because it's a simplified version of NCE, it doesn't guarantee that it approached like softmax. But NCE does guarantee approximation to softmax when the number of sample like increases. So for this example, we will be using NCE loss. Another reason why you want to use NCE loss because TensorFlow has a very nice function for it, so you don't have to write like all these complicated things by yourself. So to start, you can use word2vec starter, and there's some util to download and read in data. Let's see how it looks like. So for starter, so for util, it's like downloads the data from here. So we're going to be using a subset of Wikipedia text. It has already been pre-processed for us, so we don't have to do any pre-processing. It's downloaded here, and it's about like 30 megabytes. So yes, further util is just very things like you build vocabulary and you generate a batch. And we also be using and we also generate for dataset. We will generate dataset from generator. So that's why we need a batch gen. So we can generate a batch of the samples that we want. Okay, so we can start. So for the steps are pretty straightforward. For the first phase, you want to build a graph, and to create an wait, why is that? I think I was doing it. Let me just delete and start over again. Yeah, I was just writing it to make sure that it works. Okay, so to start, so like just like you start an iterator. So we will create a data set here. So for when you create data set from generator, you need to specify the type that we want. So because we are inputting the indexes of the word in the vocabulary, so which is an integer. So for the shape should be a batch size and batch size minus batch size 1. This like additional dimension 1 is to make it compatible with NCE loss function. Okay, so after we get the data set, we just create an iterator and we just create an initializable iterator. And so our input now, so we have, because it's skipgram, so X is going to be center word. And Y is going to be context word because we're trying to predict context words from center words. So we just have like the next. So for weight, so in this, for this task, actually the weights that we care about because the weights return the embedding matrix for us. So we create a get variable. Name it embed matrix. What is the shape of it? So what is the shape of embed matrix? So the number, what is the number of rows? Is the size of our vocabulary, right? Because we want each word to be a row. And what is the number of columns? Yeah, so the embed size. Right. So yeah, so I define something here. So we're gonna deal with like 50,000 most popular words in the vocabulary, and we have the embed size equal like 128. So we're just gonna use like random uniform initializer. For bias, oh no, we don't have, sorry, yeah. So for inference, so it's not exactly inference, but it's more like after we have the embed matrix and we have the indexes of the center words, we would like to get embedding, the current embedding of the center words. And we can use it using the embedding lookup. So let's say, so embedding lookup, the first one is a matrix, the embed matrix. The second is just the index, which is the center words. And we can name it embedded, maybe. So we need to define loss function. So for loss function, because it's approximation, so we need to have some weight and biases because it learned a good approximation to softmax. So here, so for NCE weight, we have to declare shape, and shape is in this case is like vocab size, and this is like embed size, and initializer. So we need to use truncated normal initializer. So like with just like a normal uniform, a normal distribution, it gets like every. It doesn't matter like how unlikely element is. With truncated normal, it only get elements within 2 standard deviations from the mean. So people have found like that should be more reliable than initialized NCE weight, which is like normal. And by default, we just get a mean 0, and let's try this value. So make it scalable with the size of embedding. And we also had to create NCE the bias as well. For the shape of n, we're just going to use vocab size. We don't need this, so it's negative. For loss, NC loss function, we're just going to use off the shelf NC loss. NC loss, so first we have to pass in the NC weight. So what is going to be the labels for the loss? So we're trying to predict the context words from the center words, right? So our labels are actually the context words. And our inputs are embed because because they are actually the embedding of the center word. And we need to specify because it's a sampling based approach. So we need to specify how many elements we want to sample each time. So we need to specify the number samples. So we already have a constant here. So I think we will found it to 64 is a good number. I think like anything around like 45, 50, 60, okay, that's good. You also like need to specify the number. There's a number of classes. So what is the number of classes in this case?
The vocabulary.
Yeah, this is the vocab size, right? The number of elements is the vocabulary. Yeah, and there's one thing because we are doing across batches. So we would like to maybe get the mean of the loss of each batch. So we can use it using a temp reduce mean. Maybe just we can name it. Maybe optimizer. Let's see, maybe use Adam optimizer. Loading rate. Loss. Okay, so now we need to initialize the iterator to the data. We also need to initialize owner variable. Yeah, I'm just gonna write the graph to WatchVec symbols, and I'm gonna execute the optimizer, and I also want the loss value so I can report it, and there's no predict here. I think that's pretty it. Yeah. Let's try to run it then. I think it's gonna take like a little bit long to run. So maybe you can just like run it at home to make sure that it's working, but I think it's working. I want to show you, what I want to show you is that I want to show you the graph of it. We already have TensorBoard open because we store it in, oh wait, how does it work? Because we, because we store it in a WatchVec symbol. Oh, it's not. Okay, wow. It's gonna look something like this. So one thing you notice in the graph is that it looks pretty complicated. Like WatchVec is pretty like one of the simplest model out there because it has only one hidden layer, and it already looks this complicated. So the question is that like when we have a more complicated model and everything just looks all over the places like this, how can we organize our model? So TensorBoard doesn't know what nodes are similar to each other and should be grouped together. So if you want to do it, we would have to group our node. We'd have to group our node by ourselves. And I think this is, Oh, I think this might something I want to show you first before I do it. So TensorFlow has really cool visualization of our embeddings. So if you can see here, after you train, let's see this one. Why is this not running? Oh, I think it died. Okay. So actually, that's exactly. So I just trained WatchVec model like this one, and then I add a little bit of code here. If you go into WatchVec visualize, you will have a little bit of code you can visualize. So what it does is that it can visualize a certain number of most common words. So in this case, it wants to visualize like 2,000 words. And so how to do it? So the first is that you have to get the embedding var, which actually is just the embedding matrix. So you get like the first 2,000 rows of the embedding matrix, and then you create a projector. So you have to tell it where you want to store all the files needed for projection. So in this case, it creates a folder called visualization. Yeah, so you just like the next thing is that you add embedding to the config file, so it knows like you use this embedding to visualize, and you can also tell it what. So like when you visualize, you usually have the dot, and you want to label the dot, so you know like this dot corresponds to this word. So just what the metadata path is, it just tell you like the labels of the most common words. And yeah, so you do projected visual embeddings and you save them in that folder. So after that, you can run it and you can see something like this. Because I did own the visualization in the visualization folder. So if I do it, I will see something like this. So I prefer, so you can visualize in PCA or Disney. I prefer Disney. So Disney takes some time to train, to stabilize the visualization. So we can, so in the process, in the meantime, we can try something like, let's say, let's just do some sanity check to see if our embedding makes any sense. So if our model works, so what it does is that like words are similar to each other, should be close to each other. So let's see like what we can try to find the words most similar to one. So you can see, oh, so one similar to like 7, 2, 6, 4, 8. So which kind makes sense, right? So we think, oh, so it's not too bad. So if you just like go to A, so you say, oh, A is close to another, that seems reasonable. One thing that I usually like doing is just like, just type in random country and see like what word associates those countries. Say, oh, British, Canadian. So it seems like a lot of people confuse American with British, or they appear in the same context. Let's say food. Oh, I think food. It seems like food is also like a lot easily relate to dynasty, health, water, property, which also makes sense. So yeah, so that's what I usually, I like doing. So, and you can also like see all of this, like you can see those clusters, and you can say, oh, what are those clusters? What do those? Oh, I think because I zoom in, so it doesn't. Yeah, because I zoom in is a weird thing. So I have to stop. So you can see all of this. So like you can see like all the alphabet letters are clustered together in this cluster. You see they all the numbers are here. So it's pretty nice. And you can also do embedding, you can do projection of anything, not just word embeddings. So if anything that has a vector representation, you can visualize them. And one thing here, for example, here is when you visualize MNIST data. So when you, each image is just 28 by 28, and they are actually just a vector representation. So you can do something like this as well. Okay, so the next step is that we want, yeah?
You're doing that for images. Is it just showing you the Disney representation for the more image vectors, or is it kind of taking some layer of the network that's learned the representation and showing you some idea at that point?
Yeah. So for projection, it uses some dimension reduction. So like for example, like for images, you might have 100 pixels correspond to like, so it has 100 dimensions. So you have to reduce it to a smaller dimension to be able to project it on the like 2D or 3D.
Well, I get that, but the thing is projecting to 2D, is it the original image, or is it some later layer in the network that's learned some representation?
I think for this, I think you have to read like the blog post to see like what exactly he did, but I think it could be just a raw representation. Okay, so the next thing is that we would like to be able to group together. Oh shoot, we have like 10 minutes. So basically name scope, what it does is that it's grouped together nodes under the same scope so that it's easier for visualization. For example, like after you group like things on data on here and on the NC stuff under some loss scope, then you have something a lot easier to read like this. So you can see that. So TensorFlow has on TensorBoard has 3 different kind of edges. So this one is it means that like for the dotted one it means NCE weight has to happen after init has been done. So it shows the control dependency. So like what ops depends on what ops. And this big gray arrows means that it transfer data from here. So like NC weight like put in data to loss, and for the orange ones means that optimizer mutate the value of NC weight, which means updates the value of NC weight. So a lot of people ask a question about variable scope and name scope. So they both create a name scope. So variable implicitly create a name scope, but what variable scope does is that it facilitates variable sharing. And I want to illustrate the problem of variable sharing with very quick example. So first of all, we have a simple 2 hidden layers network like this, neural network like this. So we have like H1 with like weight and bias, and with the layer 1 have like also have a weight and a bias. So when we call, and we have the x1 and x2 are 2 different input. So they are just like normal random normal values. So when you create it, when you call this neural network on these 2 values, we're going to have something like this. So there are going to be 2 sets of variables created, one for x1 and one for x2. And this is not what we want, because we want our weights and biases to be trained on the same. So like we want all our input to be used for all the weights and biases. So one thing is that like get variable, what it does is that if a variable already exists, then it just like recalls that variable. But if that variable doesn't exist yet, then it will create that variable. But when you replace t.get variable with t.get variable, you can see something, you can get an error. So what it means is that like for you to reuse the variable, you have to explicitly tell TensorFlow that. So you have to put on the weight on the variable under some scope, some variable scope, and then you have to reuse, tell TensorFlow that you want to reuse the scope. So first of all here, so you put on the variable under maybe like 2 layers, and then after you create, after you call it on x1, so you have already created w1 and b1 and w2 and b2. You would want to reuse the variables for the input x2. So here's how it looks like when you visualize it. Yeah. So and you also notice that we have a lot of repeating code here. And one thing you can do is that you can reuse them. You can put them in nice different layers. And this is actually you're building. This actually is a building block for tf.layers, which is a higher level TensorFlow. So they just define different layers for you, and you can just call it. For example, here we just create a fully connected layer. And also, like instead of have to explicitly call reuse variable on scope, when I create a scope, I can just like pass a keyword tf.auto-reuse. So the keyword means that like if I find some if there's some variables inside that scope, then I can just reuse them. But if it doesn't exist yet, then I just create a new one. So yeah, and with this you can create like indefinitely as many layers as you want. And it looks pretty neat like this. And another thing that pretty important that is maybe we can cover in the last 5 minutes is a lot of time you have the model takes a long time to train. I think like in the class you might have some model train like up to like 4 or 5 hours. So what you want to do is that sometimes you want to stop the training and to like just extend the model, and then you want to like resume the training like nothing happened. Or if the computer crashes, you don't have to restart like everything from the beginning. So what you can do is that using a saver object that will save the current model into the save path, and when you want, and then you can restore it later on. So how does this work? So here, so you have you create a saver after just maybe like just right before you create a session, and maybe you want to save it every 1,000 steps. Then you can do something like this. So like every 1,000 steps, I just save the session. So session stores on the variables. So you can just like save on the variables in the binary file, in the directories that you specify. So global step. So when you have many different checkpoints, you would like to know like which checkpoint corresponds to what step, right? For example, you want to save like at 1,000, 2,000, 3,000. So you pass in the variable global step. So it will append at the end of the checkpoint name. So you can choose to restore at any point you want. So global step is an example of when you don't want the TensorFlow to optimize that global step because you just want it to increment like at every step tuning. So yeah, so you usually set tunable to be false. And so good thing is that like, for example, like if you want to have some scheduler incremental of the or decremental of the learning rate, so you can also tell TensorFlow. So first, like when you're passing global steps, so TensorFlow knows to update global step, like to increment global step by 1 every time you run optimizer one time. But it's also useful like when you have a learning rate, it can also automatically decrease the learning rate for you, and you can read more about it on documentation because I think we don't have time for it. So here's how it can look like, the checkpoint directory will look like. So one thing is that saver only save variables and not graph. So you still have to recreate the graph every time. There's another way, there's one way you can just reload the graph. It's like you just print out the graph definition into a protobuf file, and then you can just reload that graph definition, so you don't have to recreate the graph every time. You can also choose to save like certain variables. So by default, Saver will save all the variables in the model, but you can sometimes just want to save like maybe like a weight as this layer, another weight as like that layer, and it's really useful for a lot of pre-trained model you see online. So you just want to get the weight as the last layer, like as the logist layer. So you can choose, so you can specify something like that, like I want to save V1, V2, and to restore, you just like restore from the checkpoint. So I want to restore from the step, it's actually like 100,000 into the session. You can just call restore. One thing is that like you want the model to do something like that, like if a checkpoint exists, then restore for the checkpoint, and if a checkpoint doesn't exist, then just run from the beginning. So you do a if like this, it check if there's a checkpoint in the checkpoint path, then it restore, and if not, you can just like create. And you can also use tabular summary to show the training progress. So basically, you can like visualize the loss as over the training duration. You can also show like the accuracy, or you can show histogram as well. So this is how you do it. You just like create a summary as an object and as an op, and then you execute it, and it gets a summary, and it writes it into the log file. Yes, that's basically it. So putting it together, something looks like this. You can see the code on Word2Vec visualize.py. I think it's on the class website, and it will see something like this. Here's the loss. You can see that it's as the loss go down gradually, which is nice. And you also somebody likes to see it as histogram. And one thing I find really useful is that when I have different hyperparameters, like I would like to have different subfolders in my graph folder, so I can compare them. So you see, like here's the orange line corresponds to learning rate of 0.5, and the blue line corresponds to learning rate of 1.0. So let's see which one works better. I think that's it. Thank you very much. If you have any question, feel free to email to me.